Alright, should be live and making a video. Really? I guess that's what we're really doing. And such. And so forth. And whatnot. Alright, so this is again the Bohm, okay, explanation for the double slit experiment. And this was Bell was a big fan of this, because he thought it got around at least one of the two issues regarding entanglement. So I guess I shall explain some of that. Now, the most outstanding feature you can see is the pattern doesn't match the single slit or the double slit. So you're saying they make all this stink about how we should accept this new theory when the new theory doesn't actually predict the pattern you get. So it's just an on-off pattern, and you're just saying that any on-off pattern will do. So that's basically part of this magic trick. They're saying they can pull an elephant out of a hat. Okay, entanglement, breaking determinism. This idea that there's woo in the universe. You know, your anus twitches and something twists in my brain. That somehow we're all interconnected, and it's all this wooey religion, frankly, and you all buy it and believe it, and then when you analyze any of it, this is your elephant. Your elephant is, it doesn't even match the pattern you get with light. So how could it possibly be a viable explanation for the phenomenon when the pattern doesn't match? There's no double maxima. It's a huge miss. There's also no envelope. Another huge miss. I mean, it's just so bad. So, literally, this is like, you know, them saying, you know, Jesus walks on water, and then you show up, and they have curtains, and they have mirrors, and they have smoke, and they have all kinds of bullshit, and you're saying, well, why do you have all that bullshit? The guy's just supposed to walk on water. What do we need all this bullshit for? Oh, because the bullshit is how they hide. You know, they're just doing a trick, and the trick is deceptions, lies, exaggerations, and hype to basically just sell a religion. Okay. And the religion is, whoa, there's no determinism. The universe is all wacky-versed. And somehow, because the universe is wacky, that gives us free will, whatever that is. You know, so this is, you know, and so you just, you know, it really is God particle bullshit. There really is no connection to reality here at all. They don't even understand any of these concepts as they are. Okay, so that sort of gets to a comment left by some idiot, frankly, probably, most likely. Because again, it's not an accurate statement. So it must be an idiot. Alright. Okay, who says, you once said Einstein wasn't particularly impressed by the double slit experiment and was even dismissive of it. Now, I didn't say that. Okay, I didn't even say he was dismissive. What I said is nobody paid any attention to the actual pattern. All they accepted was that light somehow did this wooey entanglement thing because they automatically bought the explanation that, gee, the things must be banging into each other and interfering. So the fact is, they sold the idea that it was interference, constructive and destructive, that was somehow creating the pattern. Not that the pattern was being created because, yes, you broke something and then you remade it again. So nobody provided that explanation, so they all just bought the default. Yeah, and that's the big mistake. So the fact that Einstein was a very poor advocate, frankly, for an alternative explanation, because I don't think he ever really recognized any details. You know, he just accepted, like everybody else, that this is the pattern, you know, and he didn't really inspect the pattern because it's so, frankly, it's so obvious when you inspect the pattern, because you're saying, what is the difference between two slits in separate space and two slits that are right next to each other? Well, the difference is the outside surfaces are much further apart and the inside surfaces are closer together. And that's the big difference. You're not combining this and this. You're making this, okay, which is very different. than two separate thises. Yeah, the little Vulcan thing was shoved in there for free. Didn't even know I could do it with this hand. Yeah, very good. It's the wrong hand. I'm double Vulcan. Alright. So back to the other thing, which requires me to remember where it was. I think it was there. Yes. Alright. Then we have to move it back into view. Alright, so I'm just saying, obviously this is just not the right pattern. And what this is relying on is there's two things here, right? So the idea is when they do this diagram of the double slit, there's two issues, all right? And so Bell was obsessed with one issue, Einstein was obsessed with another issue. Okay, so Einstein didn't like indeterminacy. Okay, that was well, he obviously didn't like he didn't like whatever he called it, action at a distance or spooky action. So he didn't like either one, and I don't like either one. I think both of them are concessions to somebody walking on water or somebody pulling a real elephant out of a real hat. I don't think it can be done. Okay, I don't think there's anything to give us any good reason to jump to that conclusion. There's got to be simpler explanations than elephants popping out of hats. All right. So there's two issues. There's superluminal, okay, and that's what they call local. So, I mean, you have to go through a whole bunch of, oh, yeah, you can't see. I have to actually provide you the camera view. All right, there's two things. So local equals superluminal, we'll say. Okay, so you maybe keep that in mind. So whenever they say local means it isn't superluminal. When it's non-local, that means it is superluminal. That means that's ESP stuff is happening. Okay, so the Bohm thing gets rid of the non-determinism, okay, in the sense that it's not saying there's randomness. Okay, they have some formula for all those squiggly little lines. Those lines represent drift lines where the actual, see, they think there's a wave function, okay, so there's there's the superluminal stuff happening, the wave function, the you could say these little pushes as it goes through time. So the particle's going through time and it's interacting with the other things with this ESP power, and that's deciding where the probability will be. Okay, where the particle will end up. You know, could be over here, could be over here. So it's going to end up in one of these locations by probability, but the probability is being caused by actual effects. So that's why it's all drawn out like that, because they're trying to imply there's actual effects that are causing it. So it isn't like Feynman says, instant, it just pops out randomly in some kind of random direction. They're giving you a cause for the probability at the outcome. But it still includes superluminal. So it's a completely non-local theory. So when they say Bohm, it means non-local, okay, but not random. And then the classical Copenhagen is both non-local and random. All right, so that's not much of a difference, frankly. Okay, it's, you know, they both suck, but those are the issues that are being argued. So whether Einstein was more concerned with spooky action or more concerned with non-determinist, all right, who could say? But those are the two subjects, and Bohm doesn't get rid of both, and Bell was comfortable with one and uncomfortable with the other. So Bell was kind of uncomfortable with something that was non-determined, okay, more than he cared about whether it was spooky action. So he could accept spooky action, but he himself wasn't too comfortable with non-determined. All right. So, you know, I've already been over it, but you have to understand there's the two patterns that they're seeking, okay, are, you know, something that would look like this, okay, and Bohm looks like this. All right, and if you're and both of these are still incomplete in the sense that the real double slit, these are single slit patterns. So this is what you get when you have a single slit. You'll get these patterns. So they're not even on the subject, in the sense they're creating a pattern for a double slit, and the double slit actually has to do this much more complicated thing, okay, where it creates this pattern. So it's not even close to this pattern where you have the two combined. And again, the simple solution that Einstein missed, okay, in terms of analysis, is just understanding the single slits make these patterns, and the wider the opening, the smaller these bars. So just understand, the wider I make the opening, the smaller the little bits, the greater the number of wavelengths that fit. And so you can understand the greater potential, okay, for a phase different in a location. So the phase differences happen much more often the wider the difference between the two surfaces. And the fact is, the surfaces are the point of which is creating the pattern. Every bit of the pattern is being created on a surface. All of the fringe light is surface photons. That's why it works. Okay, that's why the math works. And the narrower the slit, the bigger, okay, because the fewer wavelengths that fit in there. You can't have too many locations where you have constructive and destructive. If you believe in constructive and destructive, there's fewer and fewer locations where that's possible, the narrower the slit. So you can understand, narrow slit, big opening, wide slit, lots of opportunity. And what do you create when you put two slits next to each other? Two slits that have, say, a pattern this big, all right, and you put those two next to each other, what you've created are these two, this big slit, all right, which is going to make the little bars, and these narrow slits, okay, they're obviously going to make the big bars. So that's why the two patterns create this lopsidedness of the big giant envelope and the little tiny elements. But it's that easy to understand. It's right there in front of you. You have two surfaces much further apart, and you have two surfaces much closer together. And those are the two patterns you're creating. Those are the two single slits that are being superimposed on each other. And the fact is because you're adding sources, okay, just like flipping coins or something else. If you want matches, the more sources you have, you multiply the capacity to make a match. So because you have 4 sources of light, you have 8 times more light, or whatever the game is. You multiply your probability of a match by increasing the number of sources. So that's why when you close one slit, you don't see anything, and when you close the other slit, you don't see much. It's because there's not as many photons that can create a contribution, and because it's about the surfaces. So the 2 slit is the 4 surface experiment. 4 surfaces are contributing. The single slit is the 2 source experiment. Only 2 sources are contributing. So that simple explanation blows up all of it. Copenhagen, Bohm, all this stuff all goes away because it doesn't have anything to do with waves, and it certainly doesn't have anything to do with a wave function. It doesn't have anything to do with communication between the photons. It just has to do with your scattering broken pieces of photon at the surfaces. The broken pieces are flying to all locations, and there's a 50-50 chance you put them back in phase. And it's that simple. That's it. You don't need any of this talk about you just pulled an elephant out of a hat, because that blows it all up. All right. So now I'll do a little bit on the other interesting aspect of this aspect. One of the people who got a Nobel Prize for a 40-year-old experiment of dubious, substance, and that it wasn't one of the ones often repeated. And it has to do with polarization. So there's 2 aspects to how they do entanglement experiments. There's 2 pieces of data about what is a photon, right? Okay, so if I just draw this thing and say photon, it doesn't matter. I don't know how you want me to draw a wavicle. Okay, photon, whatever. It has 2 features. It has polarization and it has phase. So the two little PPs of this whole bullshit. So the phase, okay, has to do with the matching of the position in space, okay, of a photon. So this photon would be out of phase with this photon because the bits aren't in alignment. So if I was to take random pieces from this, I won't have a match in terms of it won't line up with the right frequency, right? So if I randomly chose this one, and this one, or whatever, I'd end up with an uneven frequency. I'd end up with something, you know, look like this instead of something that looked like this. So it wouldn't be able to do the same thing this can do because it has the wrong frequency, the wrong period between the events, and it's the events hitting the surface that are causing what we call a photon. Now, yeah, you have to accept an awful lot in terms of understanding that a frequency has to be made out of something, wavelength has to be made out of something. It's not like there's just some long string flying through space and the long string hits the surface somehow and the surface knows this is a 5-mile photon versus a 1 nanometer photon. Somehow it knows the difference and the surface and blah blah blah. So you really have to do some reasoning to understand the frequency matters. It has something to do with giving electrons momentum on a surface, causing them to move, which is illustrative of duplicative of electricity. The same kind of idea. It's causing an electron to move across a surface. That causes electricity, and that's something we can measure, and that's how we measure photons. Alright, so there's two things that are happening. There's the phase, and then there's the polarization. Now the polarization, I'd say, could be illustrated as you could understand a photon this way. Okay, that say it's 3 bits, 3 quanta, 3 light quanta combined, and that they're all parallel to each other, moving in this direction at the speed of light. So they've retained their frequency, their period, but they also have a distance, okay, in the sense that one hits, another one hits, and another one hits a surface, and they do it in a line, okay, a line going this way, or a line going that way, a line in some way, because they're aligned in space, okay, not only as a frequency, but as a distance between them in terms of where they're going to hit, when they're going to hit. So like, when they're produced in an antenna, they're produced a piece here, and then the next piece here, and then the next piece here, so to speak. So the first piece is well on its way before the next piece goes, in the sense that it takes time for the electricity to go up the antenna. And so that's why it has a polarization, is because it's initiated in one place, and it doesn't, the initiation doesn't get to the next location, the next atom that it's going to cause this effect to, for a certain period of time. Alright, but so you can just understand there's two aspects. There's polarization and then there's phase. Okay, so now we'll talk about optical polarizers. Not all polarizers are the same. Alright. Okay. So, the Allen aspect experiment, most of these experiments are done, they talk about spins and they talk about lots of stuff, but they're really done with just polarizing film. And the idea is you have to inspect that a little bit to understand what it's doing. Okay, so the basic idea is that, it's just a grating, okay, it's just lines, and the photons hit the lines, and it depends on which way the photon is polarized, which line it goes through. But that's the wrong way to think about it, because that's not how a polarizer works. That's how a diffraction gradient works. So what the polarizer is doing is taking two pieces of film. So it really doesn't have, it's not like the thing's going to go in here and get broken, and it's lined up and it goes through. What's really happening is just a difference in your bending, okay, in different directions. So obviously if I took pieces and I bend them, their polarization is this way. I can shoot the pieces up and I could shoot the pieces down, or I could shoot the pieces left and I could shoot the pieces right. And I think you can sort of understand if I shoot the pieces up and down from light going this way, that the bent light from a photon oriented down here, and the bent light here, and the bent light here, and the bent light here would still all be able to mix on the surface. All the pieces would still be in a line, and I would be taking pieces that were getting deflected up, and I would be matching those with pieces that are deflected down. So they'd all be still hitting a tiny bit of surface. Whereas if they're bending this way and bending that way, I'm not going to be able to put those photons back together. They're going to be hitting a hugely wide area. So if all the light is this way and I'm shooting, scattering pieces in all these directions, I'm not likely to get this back. But if I shoot the pieces up and just down, then you can see how it's likely I'm going to get it back again. So the fact is, the polarizer that this light will go through is bars this way for a diffraction gradient. Okay, so as I illustrate, if I put the light through this way, you can understand that all these little bits, right, and these are just bits, these bits would just go this way or go that way. So they'd all hit a surface that would be this size. Where if I have the photons polarized this way and I go through, well, then these bits are going to get shot in this direction and this direction. And so when they hit the surface, it's going to be a wide area that all these little pieces will be hitting. It'll be scattered over this huge wide area. So I'm not going to get these. I'm not going to be putting the photons back together. Very low probability that I'll be able to put them back together, whereas very high probability if I go in opposite the polarizer. That's for a polarizer made out of bars, okay, surfaces. Surfaces diffract light in these directions. Now, a polarizing film that's used for light, it only has one feature in common with the grating, or the diffraction gradient. It's not a diffraction gradient. The optical polarizer, okay, is films, layers of film. All right, and what you're doing, so it has some lines to it, but the lines aren't diffraction lines. All right, so what it is a layer, a substrate of clear stuff, and the trick is when light goes through it, the phase is changed. That is, the light has a problem getting through it, is slowed down a certain amount, which is a phase of the light. Now, why it's exactly a complete phase, who can argue? I'm not going to argue that in this video. But the idea is it just shifts the phase. Okay, so the light's in this phase, and it's going to shift it to be this funky phase. Okay, so the light goes in this way, and it's going to come out this way. So it's going to be a shift in the positions. And the positions will be 1/2 a wavelength shift, which is going to be a off phase. So it's changing the phase from on to off, you could argue. And then they put a second layer on in bars. So it's bars of a second layer. So you can understand the idea that it confuses people. I mean, there's stripes. So it looks like stripes again, right? The distinguishing feature is stripes. But the stripes aren't doing the same thing. They're not scattering the light. These bars don't create surfaces. All right, they're just they're changes in the thickness, or the changes in the chemistry of the material. So they're not surfaces. It's not like there's a bunch of surfaces that are going to diffract the light. It's all they're going to do is add another phase change. So they'll change the phase once to get the 90, and this second layer will put it back to 180. So you can get the idea that what it's really doing, it's detecting the polarization, right? So it depends on what your polarization going in will be affected by the phase change. So if your polarization is one way, you're likely to get phase changed, right? And if your polarization the other way, you're less likely to get phase change. So I guess you could say it's doing both, diffracting, okay, and changing the phase. That would probably be the more accurate way to say it. So he probably shouldn't have said it doesn't do any diffracting, because it still has to screw the light up in some manner to make it less likely that you're going to get the light back. So you can sort of understand that you're just you're changing a feature based on its polarization will change its phase, and so you're connecting phase to polarization. But the key fact is what you're really doing, the big thing you're changing is the phase of the light with the polarizing film. And it's the change in the phase that's making the photons visible or invisible, and it's the one that's changing whether the photons you put through the polarizer was one way or the other way. So the other trick of polarization is that it's not 50-50 over 180 degrees. The polarizer, the film, is only blocking or allowing through this. Okay, so you could be oriented this much. You can have this much change, all right, in your position, and you go through the filter. All right, so the filter oriented this way lets these photons through. It's not like anything in this direction. It has to be just this part of the, and the other filter is blocking this section. Okay. All right. And so the distinctions are as these pi sections overlap. That is, you could do this, you could just change the original orientation of where I established that circle, and I could just turn that, and now this polarization will overlap that one. That is, if I bend this section down, half of these photons are still fitting that orientation, and the other half will be here. So I've got half are still, well, I shouldn't have put it down there. I should put it up here. Okay. And so now it's this pi section that lets it through, or it could be left, right, this way. So all they're doing is playing a game where the truth is that whether it's this way or this way does matter. It's not the same thing. Getting through and going this way and going through and getting this way are 180 or 90 degrees difference between those two outside photons, but it's a real difference this way and this way. The fact is, the detector, okay, will function differently when you put another film in based on whether you were this way off or that way off. So if I had another film that's going this way, it matters whether it's going this way or I put it in this way. It's two different sets of photons. One way will reorient this one, and the other way will reorient these photons. So it's a different set of photons that you're going to reorient, and it's a different set of polarization. So that's why they get these numbers that don't match, where they're supposed to be getting 25% of the photons and they only get 20% or some other thing. And this is where, Bell's contribution is really quite minor, in the sense that all Bell's really saying is, if your expected answer is 50 and you get an answer of 25, there's no chance, okay, there's not some huge error, and so it's impossible. Essentially, it's impossible for the prediction of 50. It's impossible for there not to be some cause if it comes out 25. So it's not a very bold statement saying that you can be outrageously off, but you can't be insanely off and call it an accident or a possibility. If you're way off, then something else is going on. And so that's all they're justifying the entanglement on, is that they've predicted a number based on their wrong understanding of how polarization works. Okay, and then they don't come up with the right number. And so they say, well, the only possible explanation is woo. The wooitons had to woo and do something crazy to cause this malfunction. And it's really that simple. So they're just, it's not like some glaring truth. So this is how bad their magic trick is they're just basically saying, look, the experiment didn't come out as predicted, as classical mechanics would predict, so we have to come up with some bizarre explanation, when the explanation is they don't know the difference between left and right. They don't know that a photographic film, a polarizing film, doesn't work the way they think. It doesn't kill photons. It doesn't block photons. It breaks the photons. It's clear film, okay? This film is clearish, okay? It's not 100%. That's part of the problem. It does kill some of the light, 5 or 10%. But the point is, it's clear, okay? You're not blocking photons. You're not stopping photons. You're not absorbing photons. This material does not get hot, okay? There's no evidence it's absorbing the energy. it's passing the energy, but it's doing two things. It's breaking the polarization and it's breaking the phase. And you just have to understand in what orientation it's broken it the most. And that's all they're doing, is screwing that part up, so they're getting a wrong answer, a wrong prediction, and saying, well, we have to have, the only way we can explain this wrong answer is we have to invoke God and angels and gremlins and voodoo. No, you don't have to. Alright. So that's where I am so far. I'm going through, I'm trying to find whatever I can to provide any truth to this whole conversation. So this Bohm thing, okay, we'll go back to that, is related to de Broglie and this some other guy, whatever his name was. And it's all like it was manufactured in the 30s, 1930, somewhere in there, first proposed. And you know, it's not even mentioned, frankly, in the classical. You won't even. I don't even think there's a mention of it in a Professor Lewin video, or you know, in most college explanations. They don't even. Maybe in the 4th year or 5th year or something, they might get to it, but they don't bother with it in terms of even having a conversation about this alternative explanation for the double slit experiment. They basically just teach the Copenhagen crap, the randomized Huygens kind of bullshit. And that's it. This is sort of Huygens-esque, frankly. I mean, that this really is turning again. The light goes through the slits and it turns into a trillion little tiny, you know, whatever, wavelets of some kind. And it's, you know, so we're back to a bunch of wavelet math. But the point is that this explanation gets rid of random, so it's anti-Feynman, but it keeps the idea that the pilot wave is going at superluminal speeds, and the particle is just going at the speed of light. So it still has that hugely negative feature, but it gets rid of the non-determinism because it has a history. You can go back in time and explain why the photon lands at a position no matter how far back in time you go, all the way back to the slit. Alright, so I think that's probably enough show and tell. See if there's any comments, and then maybe we'll just leave it as a video. I mean, it's really irritating going through all this crap, because the stories are just stories. I mean, none of this is ever connected to something real. They just say, look, it's a perfect, you know, this perfectly explains the double slit. It's nowhere close to a proper explanation. It's not the right pattern. I mean, it's just plainly not the right pattern. How can people put this up and say, look, this explains the double slit? It's not even the single slit pattern. And so we're right back to the whole Thomas Young drawings. Don't produce the right pattern. Who cares? That's part of the story here, is it has to match the pattern. Oh, now, why would we bother doing that? Actually matching the actual pattern? We don't need to do that. We just have to create a pattern of any kind. Any kind of pattern proves we did it. I don't even know how to compare this to something, but this is like them saying if we were, you know, they make a projector that makes light on a screen, and then they say that's a movie. You know, it's not exactly the same thing. It's so bad. So very bad. Alright, so let's see what's in this chatty thing. The law of Newton. I mean, can you explain the law of Newton? There's no law of Newton. Newton's laws of motion. Well, you know, they're not very well articulated. But they're basically just saying something's moving, it keeps moving. Okay, that's not too surprising. We see that all the time until something else hits it. So yes, if you give something motion, that is, you hit it with something that makes it move, I would argue it's absorbing a force. That is, it's changed, okay, by the interaction in terms of what's where the vectors are pointed inside of it. So it has little vectors inside of it, and the vectors are pointed in a direction, and you can change those directions through interaction. So two things make contact with each other without being connected to my hands. Okay, if my hands weren't connected, they make contact with each other. The contact means they exchange their condition. All right, and the more time they have to do that exchange, the more likely they go off in the same direction. And the less time, that is, it's not very elastic, then yeah, they take a portion of each other's identity. So, if this was made out of lead and this was made out of watermelon juice, some of the watermelon juice gets in the lead and some of the lead gets in the watermelon juice. Not too outstanding. The second law is they pervert it into the F equals ma thing, when really what Newton's is just saying is the force equals momentum. The force is momentum. It changes your momentum completely proportional. So whether you get hit by a force that's in free space, like gravity, or you get hit by an object that contains force, it's all the same thing. The only thing that matters is the mass and the velocity. So if you want to find out what the energy of something is, you just say what's its mass and what's its velocity. So it doesn't matter whether it's an electron or proton or it's an elephant or it's a galaxy. Just add up its mass, find out its velocity, and you know how much energy it has, how much it has to interact with the rest of the world, how much watermelon juice there is, how much capacity to change something else there is. And then the third law is just the equal and opposite, which is dangerous. So the simple explanation, that is sort of a Newton failure in my opinion, because there's no equal and opposite. There's no counter force. Friction isn't a counter force. Friction is you contacting something and giving away what you have. You heat the ground with friction. You lose your energy, it gains the energy. When a bowling ball hits a bowling pin, there's no equal and opposite reaction. The bowling ball loses velocity to the pin. It gives the pin its momentum. Okay, its arrows pointing in a direction push arrows in the other object, which means its arrows no longer can push. The thing pushing moves from one object to the next object. So it's like the Newton's cradle. The Newton's cradle, one ball has the little arrows. It hits the other ball. The arrows just jump right into the other ball takes off. If I make the masses uneven, then this one's deceleration won't match the acceleration of the other object, and so the contact won't be sufficient for there to be a complete exchange, and it'll only be a partial exchange. So either they both go off in this direction at different speeds, or this one reflects and this one goes this way. So you have an uneven exchange if the objects can't accelerate and decelerate at the same rate. But the real key is the explosion argument. So you have all the other cases of equal and opposite just have to do with conservation of the momentum. You can't make new energy and you can't lose energy, so you have to follow where the energy goes. So that's all it's really saying. It's just the conservation law. The Newton's third law is basically just saying conservation of momentum is a law. You can't kill the momentum. You can't. So if the mass, you have a big V and a little m, you can convert it into a big M and a little v, or vice versa. But you can't lose total momentum. And the key thing that makes everything a little strange is the explosion. So the explosion, something explodes, obviously it's exploding the same this way and that 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 way. It's a molecular explosion, and the explosion just means an expansion. And the expansions are always multi-directional. Nothing supernovas in the small universe. Nothing excretes energy in one direction. Each little atom, okay, let's say you're going to lose an electron in one atom. Well, the electron leaves in one direction, and the atom it left from goes in the opposite direction, right? But if you do that for 1,000,000 atoms, each one will shoot in a different direction. And so the point is that the explosion will be even all the way around. And the only way you can change those rules are like with a rocket ship, you can make engines, okay, that force all the energy going sideways to go down instead. Or you can create laser beams and force energy going in random directions to go in one direction. But you have to create a mechanism to steer the energy to break Newton's law. And you're really not breaking it, because every time you steer it, you cause another opposite reaction. So even if I go to the moon and I use the moon to come back to the Earth, that is to do a U-turn, I have to steal the turning energy from the moon. So I will change the moon's orbit by using it to change my energy, change my direction. So if you're going to change direction, you're going to have to give something else your direction. So there's conservation of direction and conservation of the existence of energy. So both the direction, the angular momentum, you could say, has to be conserved, and the power of the energy, the fact that it exists, has to be conserved. Yeah, that's pretty good. An acceptable answer. I guess I can just leave this up. I won't bother popping it out, and I'll just move that over. So that's what we got so far as comments. Not much. So you got a couple minutes to say something else. Let's see, what else do I have to say? I would play the, I don't want to change subjects, go to, the space-time stuff. Kind of like to stay somewhere near the subject of the polarization and phase. And that's what confuses this subject, because they talk like they're just measuring spin, or they're just measuring some function, and then they can do all this up and down arrow stuff and say how it can only happen this way because of entanglement. But they're really overlapping two subjects. The polarization subject goes this way, and the phase subject goes opposite that way. And so that's what's confusing the subject, is when you're talking about an entanglement experiment, it's changing two features of the photon, both its polarization and its phase. And they don't account for that. Again, they don't account for the fact that their theories don't match the actual pattern. Their wave theory doesn't work. It overtly, profoundly fails to predict the right pattern, and yet they call it the most successful theory in the history of science. I mean, that's how much they care about the truth. So, you people who are just so eager to defend conventional science, you really should be able to concede that there's so many places where they just cheat the truth so aggressively that, how can you keep making defenses for this really bad science? They don't repeat experiments. They didn't repeat the Eddington experiment with better technology. They don't really show you proof of anything. They never show you a quark. They never show you any of these subatomic particles they say exist. You'll never see a gluon. You'll never even see a reasonable explanation of the existence of one. You'll just see a cartoon drawing. Let's see, maybe I'll hit this little arrow, but I don't think it should matter. Nope. Yeah, just move things in the wrong direction. That is funny. You hit it and it just changes the view in some negative way. Alright, so yes, 10 people. Alright, not too many. So, you're running out of time. Type something or interact in some useful manner. I will concede that you're incapable of participating constructively and be on my way. Alright, I'll concede. So anyway, till the next time and such, I don't think there's any new comments, so I'll just check quickly to see if there's anything new on any of the videos, which there probably isn't. Nope. Alright. So we'll just clean up and get out of here. Alright, so till the next time and such, this has been draftphysics.com, debatephysics.com, also video presentation. So, goodbye. Yeah.